Alrighty. Can you guys hear me down in the cheap seats? Excellent. Well, thank you, folks, for turning up at the slightly unusual time this afternoon. So today I'm going to run you through basically the program of work that myself and a collection of folks that are sitting in the room have ahead of us over the next few years. And that's looking for something that wasn't there in particular. Basically, when can we go and find times or places where the ice down in the East Antarctic Ice Sheet wasn't in the particular part of the world where it is today? So, which is a bit of a challenge. So, for the obligatory background slide as to why we bother, obviously ice in Antarctica up until about 2000 was relatively stable as far as we can tell in terms of ice going in versus ice going out. But after that time, things shifted and we started to lose fairly substantive amounts of ice in the order of 2,000 cubic kilometres over about a decade there. And the pattern of that suggests that this is largely due to warming of the oceans surrounding the continent, and particularly those warm waters coming from the deep ocean out onto the continental shelves in these parts of the system, and then getting into the grounding lines where the ice meets the bed and starting to melt the ice from underneath, which effectively decides why we have a pattern that looks like that. Partly because this is where that warmer water has started to interact with the ice sheet predominantly, but also where we have quite deep troughs in the bed of the ice sheet. So these large subglacial basins in West Antarctica and also this part of East Antarctica. And collectively, those hold about 20 metres of sea level equivalent. And there's been, I probably don't know just how this particular community, but there's been substantive amount of concern, especially around the collapse of the West Antarctic Ice Sheet, which holds about 5 or 6 metres of sea level equivalent over the next few centuries. So for East Antarctica, which is the part that Australians tend to play in, which is the part basically to the east of the Transantarctic Mountains. So this larger mass here, which is in the order of 60 metres of sea level equivalent. There's about 20 metres of that in these basins, which are susceptible to future change. And at this point, we really don't have an idea of how much or how quickly that ice is likely to disappear. So models, as you can see on the left-hand side there, let's say variable in their projections of future change. And part of that is projections around the IPCC scenario, which is the colours. But you can also see there's difference in projections just based on the model. And that could be anything from effectively no change or even ice being taken up by East Antarctica due to increased snowfall, through to losing upwards of 5 metres of sea level equivalent over a couple of centuries. So it is substantive both in human and ecological terms. Now, because of that challenge, a couple of years back, the ACEAS funded a collection of large, basically national scale research programs. And this was the one which was largely focused on the ice sheet itself. So the Australian Centre for Excellence in Antarctic Science, which was a collaboration through a whole bunch of different universities around the country. Particular nodes at the University of Tasmania and ANU and UNSW, but also collections elsewhere, including here at UC. Initially starting off at a 4-year program of 20 million cash from the ARC, plus significant contributions from other partners along the way. And we've since had small extensions to that, and it probably will continue to extend due to some logistical challenges due to getting down there. So it's a large group. There were 40 PIs, I suppose 40 CIs across those different institutions. And as usual, probably most of those people look a fair bit older than the photos that you see up on the board. Effectively every one of those is also doubled or tripled in terms of the size of the centre. because there were an equal number of postdocs funded, and there are also substantial numbers of PhDs and other students associated with those each of those researchers. So it's a really broad group spanning effectively from oceanography to hardcore ice sheet science through to particularly goes geoecology within, especially in the oceans, for a lot of those folks. So, as is usual in these larger programs, we've been split ourselves up into smaller groups, and there are three larger programs within the centre, ranging from particularly large scale but shorter time, which is program 1. So looking at effectively circumpolar programs, particularly around modelling in that program, down to the sub-regional scale processes where we're actually going to get out into the field and measure stuff. And most people are either stuck in one of those or spread across two. And for my work, it's largely in program 3, which, as you can see there, is looking at the risk of ice mass loss from key subglacial basins over the next decades to centuries. So those large areas where we've got ice that's grounded below sea level and is susceptible to the warmer water which is impinging on the continent. So this work has really, or this program, along with its sister program, which is funded out of Monash, has really been, I guess, program defining for the logistics that's the field logistics down in Antarctica and with the Australian Antarctic Division over the next 5 to 10 years. And within our centre, the larger programs are focused on that Denman region. So it's an area off to the west of Western Australia, and in between Davis Station, which sits about here, and Casey Station, which sits in that one. And it's one of those large areas where we have the ice grounded in some cases, several kilometres below sea level. And there are two large field programs that have been funded through the centre. One of which is the terrestrial campaign, which is happening this season, but got set up last year and will continue on into next year with some geophysical observations, which are being basically put in place and left in place. And then also a large ship-based campaign looking at the oceanic component of that, basically directly offshore through the Noena, so the Australian icebreaker. But also coupled with two large German research programs, which are called EASI, which is East Antarctic Stability, and I forget what the I was on that one, but basically two 90-day cruises of the German icebreaker, heading from Cape Town into Antarctica, back up to Hobart, and then vice versa. And all focused on trying to understand effectively the fate and the future of this particular part of the world. On that one. So, what's my role in the centre? Well, I started off as a CI, and then as we were starting to develop the field program, there was a call for basically a coordinator of that field campaign, and I looked around who else was there and who'd seen a program like that one, and it looked like there probably wasn't anyone apart from me, who was basically a first-year PhD student at the time. So I put my hand up for that role, and turns out I didn't do a bad enough job, so also then got subbed in to be one of the program leads for that group. Also, given the role that I've had with the German Antarctic program over the last decade or so, I was invited on one or both of those cruises as well, but they ended up all being scheduled at the same time. So I've ended up being more of a bridge rather than a participant in those larger cruises. So that's kind of the larger scale basis, and just to give you a sense that it is a really exciting time to be working in this space, despite all the doom and gloom that has basically bounced around the media over the last few months with the Antarctic program, because in terms of actually getting out into the deep field and working in these areas which really matter for the fate of the ice sheet, it's probably the biggest thing that I've seen in the most focused research that I've seen put into this region in the 20 or so years that I've been working in the area. So it is a substantial investment by the Australian government and also by the German research foundations. And so personally, as of this summer, I'll be flying down to Casey and then out to Bunga Hills here, which is basically a fairly large ice-free area, about an hour's plane ride west of Casey, where we have these large glaciers feeding into a large ice shelf, which sits basically it's that floating ice sitting on top of the ocean in that part of the world. And there's a small Australian summer research base there, Edgeworth David, which has had a few apples previously and will swell to in the order of 40 or 45 people over the summer, which is as much as I think it would have, as that base would have seen in the entire time since it was put in the late 80s in terms of collectively. So it's a really big effort, both logistically and also scientifically in the region. So why would we care about this spot? Why is it interesting? Primarily because it's a place where we haven't got a lot of information, but also because it's a spot where there are really deep subglacial trenches looking from the ocean here and on this spot here that track back inland. And as you'll have seen through previous talks by Matt and other ones of my students over the last couple of years, wherever you've got a deep trough, it presents an opportunity for the ice basically to interact with the ocean. And in doing so, it's an opportunity for that seawater to get right into the deeper part of the ice sheet and potentially melt it out quite quickly. And that's, by quickly I mean decadal to century and potentially millennial timescales. Losing in this area upwards of about 1.5 meters of sea level equivalent. So it is globally significant in that sense. And from a scientific point of view, rather than just why would we go there point of view, in terms of the societal point of view, it's also the area of the continent where we're getting the most rapid melt at the grounding line. So partly due to the depth of the trough potentially, but also for reasons we probably don't understand because it's so poorly, this area is so poorly explored that we don't even know what the topography of the shelf looks like further offshore. Basically, once you go into the ocean, we have no idea even what the structure of the region looks like. So not really understanding. We don't really have a good feel for how water is getting into that grounding line to melt the bottom of the ice sheet, and whether there are particular features that might enhance or otherwise that flow. So, coupled with that really rapid melt, we're also seeing quite rapid thinning of the region in there, and particularly along this large glacier which chugs out along that trough and heads out through the ice shelf, and where it eventually breaks up into to icebergs. And the shelf itself is also starting to collapse in places. So it's a dynamic area that is both nationally and globally significant in terms of sea level rise, and one that we don't understand particularly well. And from the perspective of someone like me, who's effectively a paleoglaciologist, it's also an area where we could effectively put all of the different tools that we have available to us to understand these regions, just because it's got a quite complex geography about it, to the point where I've been working in this area for probably the better part of 10 years now, and I'm still learning stuff about the geography and the ice dynamics in the region. So it is, quite an interesting area to go play in. So in terms of the overall broad ACEAS component, so what are we trying to do when we're out there this summer? So we have 4 main work packages with those 2 overall goals in terms of looking at the risk of ice loss and what's the consequence of that loss. So what will happen not just to the global ocean in terms of raising up sea levels, but also the local ecosystems and local oceans and the dynamics of those areas. And so that's split up into 4 major work packages. the first being basically what's happening at the surface of the ice. How much snowfall are we getting in different components of the system? How much melt we're seeing in the areas where melt tends to occur, which is typically down towards the grounding line. Here, where the ice is starting to decouple from the bed and starting to float out into the ice shelf. And how has that changed over the last 500 or 1,000 years? So looking at ice core records to try and understand whether or not the things that we're seeing in the modern record are consistent with what we've seen over time, or whether the changes that we're seeing in terms of ice lowering in that area and mass loss are driven by some of those, I guess, more changes in the way snow either gets deposited or blown around the system. The second major component is looking at basal melt. So this is basically looking at where we're getting that water coming in off the continental, from the deep ocean, in under the continental shelf and into the cavity of the ice shelf, and then melting at the grounding line before disappearing back out as effectively glacial meltwater out into the ocean. And we're looking at this in a couple of different ways. So one, putting some basically downward pointing radar, which you can see up in this in the image there, effectively shines a radar down to the bottom of the ice shelf, and then that reflects back up, and we can monitor over time how much is melting and what might be driving that melting. So is it seasonal? Is it episodic? Are there particular events that you might be getting outburst of water from underneath the ice sheet, which are driving those events, and understanding where that's occurring. So that's the more geophysical type approach, but we're also going to put a hole through the ice shelf, which hasn't been done in the Australian program for the better part of 15 years now. And so we've had to go and reconstruct that capacity, and then put a collection of probes down beneath the ice shelf to understand how that circulation is occurring, what the materials are in terms of basically how warm or otherwise is the water that's reaching the grounding line in that region, and can we pick up any change over time? So by taking sediments off the base of the shelf, looking at changes in the sedimentation patterns to see whether or not the increase that we've seen in the amount of ice that's being lost in this system is being driven by recent changes from the marine part of the system. The next package is looking at effectively the boundary conditions of the system. So effectively, what's the structure of the part of the ice that we tend not to be able to see particularly easily from the satellite records? So that's largely geophysical, using a combination of radar, magnetotelluric soundings, and seismics to try and probe the character, even in some ways just the topography of the bottom of the ice sheet, to understand how that influences the dynamics, but also how much water is moving around on the bottom of the ice. And so putting those different techniques together allows us to ask those sort of questions in terms of what is really driving the behaviour of the flow in the region, and how may that change in future in terms of increasing or altering the flow paths of melt in that area. And then last but not least, the bit that I have a stronger hand in, and that's looking at how the system's behaved in the past. So basically, have we had past collapses in the region? And if we have, when did those occur? And what was the climate like at the time in order to drive those collapses? And I'll run through over the rest of the talk basically the detail of how we're proposing to do that. So most of what you would have seen me talk about in these sort of presentations over the last couple of decades while I've been here has been looking at what's happened to the ice from when we went from a very cold period to where we are today. And that's basically when the ice was bigger than it is today to where it got to the modern margin. And that's relatively easy because the records of that change are all areas that we can currently just walk up to, or at least put a ship over the top of, and find some evidence of the ice being there in the past. So glaciers being pretty destructive, move stuff around, they tend to leave pretty strong evidence of there being there. And examples like this one, where we've picked up rocks for cosmogenic dating, gone down the Nunatak and found basically when the ice was covering up that mountain down to where it and heading to where it is today. And that has given us quite a good understanding of how quickly we think the ice can change over time, but it's not the best proxy for what's likely to happen in the future. And that the main reason for that is because at the moment we don't have a lot of melt going on, particularly on the surface. But if we continue to push the system from where we are today into the sort of conditions that were present around the Pliocene or the Miocene, where we had 3 or more degrees on average warmer than present conditions, then we're going to start to get a lot of melt in the system, and that has the potential to really shift the way the ice sheet behaves. And that's both melt at the base, but also at the surface. And so it's not necessarily the best time period to look at in order to help constrain our ice models. So that then presents us with the problem that we need to go towards periods where we had less ice than the present day. So, and some of the classic examples of that are the Pliocene, where models and other records from sea level rise around the globe suggest that there was 20 meters of sea level rise globally at the time, and that some of that has to have come from this part of the world, but we're really not sure where and how much. So, and the Pliocene is basically the last time when we had the equivalent CO2 than what we do today, and there was about 3 degrees increase in global temperatures at the time. So, but as you can see, we're looking at areas where the ice no longer is. So we're looking at basically trying to find something that wasn't there at that time, and that is now hidden underneath a large continental scale ice sheet. So that's tricky. So there are a few different ways or places we could go to try and do that. The classic one, and the one that's, I guess, been most widely applied so far, because it's where we've already got records or sediments or our ability to get that material, is basically to go to the deep sea, where the ice sheet has been scraping off material and then dumping it out into a more or less continuous record out in the deep ocean, and hoping that during previous periods where you might have had less ice than the present day, that there's different rock types or different conditions inland of those areas. And because the ice sheets tend to scrape most significantly in the areas near their margin, if you've got different rock types in those different areas, you can, the sediment that's being dumped out here at that stage is largely derived from those particular spots. But there are a few problems with that, and you can basically go and then record through those sediments what was where the ice was at any particular time. The couple of issues are that, one, we don't really know what the bedrock is like underneath the modern ice sheet. And also there's potential that, particularly in these areas where you've got those really deep troughs, that sediment might just get stuck in intervening spots and then reworked later on, so that the record that we're getting out here is not necessarily the most reliable. But it certainly is going to be one of the more continuous records. So for me, the more satisfying approach to that is actually to go into this area here, in between where the ice is today and where the ice was, and trying to come up with a record or a proxy of something that gives us an idea of when that occurred and why, or basically how much it disappeared at the time. Probably the easiest thing to do, or the thing to do that most with the most certainty that you're going to get a result, is to go to a spot where you've got a mountain like this one, that's been buried by the ice today, but would have been ice-free during that period, and take a piece of rock from that through drilling. And that's starting to be done in other parts of the world, where particularly places like Greenland, it's been quite high success stories on that one. and basically take a piece of subglacial rock and using the sort of techniques that we use to date ice sheet retreat during colder periods, you can also get it do the same thing when it's been buried under ice. The trick is though that that's really hard to do in terms of logistics, and it's really not set up for it's not something we can do with the sort of the scale of the logistics we have available to us within the Australian program. And so because of that, it's probably not something that we're going to do in the next 5 or 10 years. But it is something that is going to get you science and nature papers. So it's something that other programs are certainly pushing towards. And potentially, if we can invite other programs to help out with the logistics, that's where we'll make those advances in this area. So we can't just spend a whole bunch of cash and devote a whole bunch of resources. So we need to be smarter about that. So, and over the last few years, I've been basically wondering whether I should keep doing the sort of work that I've been doing, or whether I should think about ways to basically to go out and be a bit more clever about how we take our samples and try and figure out how to answer these questions without that same sort of scale of logistics. And for this particular set of work, there's basically 4 ways that I've managed to come up to try and achieve that goal. So ranging from things that we've done before, which are looking at windows through the ice shelves where we getting sediment deposited in lakes or epishelf lakes or relative sea level, through to these have quite a high chance of success, through to things that are a little bit more I guess scientifically or logistically risky in terms of how effective they may or may not be, and I'll run through those over the next few slides. So in terms of the relative sea level records, so if you've got a bunch of ice that sits on a continent, then that the sheer weight of that ice is enough to depress the crust, and in doing so, you get a record by looking at things like these beaches that you can see in here of relative sea level. So if there's ice there, pushes the crust down, and then relative sea level is quite high. So this period here is when there would have been quite a large amount of ice in that region, and then we've lost that ice, and that the crust is then rebounded, and so you then basically deposit this series of shorelines, and we then have the modern shoreline at the bottom there. So by dating those beaches or through lakes that are close to those basically at those levels above sea level or below, we can get a record of what that relative sea level look like, and by comparing different trajectories. So the red one would be if we just lost ice during the last ice age at about 20,000 years, versus the blue one where if we'd had a retreat of the ice sheet back beyond where it is today, and then a re-advance to where it is. So over the last few thousand years, if there'd been a bit more dynamic behaviour, then you'd expect to see that sort of thing. And this is something that we have been doing for the last few years around Casey Station, and have been getting some pretty interesting and exciting records out of, which end up looking a little bit more like this one rather than this one, and pointing to quite a dynamic ice sheet in that part of the world. The next bit, the next technique that we are looking at using is these epishelf lakes, and an epishelf lake is basically an area of the ocean, or at least an area that's connected to the ocean through the ice shelf, which is in this area it's the green one. But doesn't have continental ice sitting over the top of it. So it's quite, and typically will melt out around the margin during the summertime. So it's quite a specialized piece of geography in that, as you can see here, you're getting that connecting, and water can come in and out, and you're getting that tidal motion. And you can see the evidence for that in this tide crack where the ice is cracked at the margin where it reaches the bedrock. And by sampling sediments in those areas, we can get a sense of has that system been stable or not. So has that ice shelf been present, and has it been contributing things like sediment or changing the character of the water column in that area across particularly the last 10,000 years. So and there's a few of those scattered around this region, which we're hoping to pick up during the summer, because it's relatively simple to go and collect those sediment records. And there have been other examples around different parts of Antarctica where that's been used to record the presence or the absence of a large ice shelf like this one here in that region. The next one, which is getting into the conceptually simple and the also the logistically simple, but potentially unknown as to whether we're going to get a result out of it, is looking at marginal moraines. So when we have these large subglacial basins, when the ice does disappear, you're not going to get nothing happening in that area, but you're going to get deposits of marine water in that region. So basically marine deposits putting sediment down in that area. And in doing so, that sediment tends to be quite different to the sort of sediment that you get underneath a true ice sheet. So the sort of thing that would be happening back here, or when the ice is overriding that spot on the present day. And so part of that is, well, one of those traces that we could use for that is the beryllium 10 that Matt's been playing with over the last 5 years or so. So the meteoric version, or other material like organic sediments, which you're not going to find underneath an ice sheet, like marine microfossils. And so in these ice-free areas where the ice starts to abut up against a piece of rock, it will form this moraine here, where it's basically dragging material from further inland and then bringing it to the surface. And I've sketched this out on the right-hand side here. So this is an example from Casey Station, where we have one of those moraine lines, and ice is moving from the right-hand side and then bringing material up from the base and then into this shear moraine at the surface. And so during the trip that I went down in briefly to Casey in February, we went and had a look at these sort of materials to see whether we could sample them effectively, and also what sort of whether these proxies were likely to be viable. And so there's quite a bit of, I guess, conceptual work to try and prove up how straightforward that was, because we can't just sample directly off the surface, because that same meteorite beryllium 10 is also raining out, and so will contaminate that material. So it turns out by dragging a ground penetrating radar across the surface of the ice, you can get quite good evidence of the structure of what's going on, where that basal material is coming up to the surface. And then taking a shallow corer, basically drilling down to below the level of where we're getting modern melt influencing or interacting with the surface, can pick up ice and come up with a pay dirt of basically the dirty ice that's effectively pristine, but we've been able to drill just with a hand drill at the surface, and we can do in multiple places along the margin in the space of a day or two. And at the moment, we're still processing those samples to find out whether or not that is going to be as successful or as otherwise as I'd hoped. The other component that I've been looking at, and this is one of those ones which is conceptually quite solid, and so if we manage to get the samples, will be a real win. But is logistically a bit more difficult, and that is using this rapid access isotope drill, which was basically put together by our colleagues over in the British Antarctic Survey for collecting ice chips. So it doesn't give you a core, but it just gives you chips, but can get you down to the base of 3 to say 600 meters of ice within the space of a few days. And as you can see, the amount of equipment that we're looking at here is a lot less than the sort of American style drilling campaign that we saw in the earlier slide. And so I have been testing up basically ideas of thinking about how we could deploy that drill in a way of recovering material from the base of the ice sheet in situ that would give us an idea of when the last time the ice had retreated back inland from the present day. And turns out the sort of materials that we've been working on in either the marine environment, like the shallow marine environment, or in the lakes surrounding the margin, are exactly the sort of materials that drill can potentially recover. So it's fine-grained sediment that we can basically pick up by drilling through the ice sheet. And we don't have to have basically a rock drill to do that one. And so while you think that the ice might basically destroy everything that everything as it goes across those areas, we have really good evidence from the areas basically seaward or ice over the modern margin that are ice-free today, that we know were covered by the ice 20,000 years ago, that have preserved sediments from before then. So they're basically quite reliable targets if we can find depressions where fine sediment might have been accumulating in those areas. And the reason why this works is because effectively the ice at the very close to the margin tends not to do too much work on the bed. So you get a lot of snow accumulate in the area immediately downwind of where the ice is moving towards, and then starts to basically protect those sediment deposits as the ice degrades over the top of it. And all of the deformation and the erosion, at least in that first 5 or 10 kilometres from the margin, happens up in the upper sort of the middle to the upper part of the ice sheet. And so the stuff down at the bed tends to get preserved. So we can stick a drill down through some of these relatively shallow areas, so sort of 200, 300, 400 metres thick, and try and target some of that material at the base. And fortunately, the area that we're going to has had quite a bit of work with some area geophysical surveys, basically looking at ice radar across those regions. And there are lots of low points where we are inland of the modern day, but potential targets for that drilling. And some examples there of where we've got some of these depressions along those survey lines, which would be targets for that drill program. And also what tends to happen, which is incredibly lucky, I would never have thought of this before I started looking, but the character of the ice surface is actually gives you a clue of what's happening at the bed as well. So not only can you get that sort of 2D slice, but we can get a 3D or a 2D surface as well to get an idea of basically what the underlying topography of that ice is, just from looking at the ice, the height of the ice surface and how fast that's flowing. And in the region that we're headed to, there's a couple of really good targets within that area that's within range of our basically that shallow drill. And those things sit immediately inland of basically depressions that we can see out in the area which isn't covered by ice in the modern day. So that's so basically that's the different ways that we're going to try and approach the problem and push this science forward in a way that hasn't really been done either in this region or even across Antarctica in those areas before. And that's pretty much where I wanted to get to with this one. Hopefully that's given you a bit of an overview of what we're looking at. There's a few other things that we will get in terms of information on behaviour of the system, which are probably areas which I'll head into the future as well. So some of the work that we did looking with the radar this summer showed that there's actually quite a lot of dynamic behaviour around that margin, particularly melt processes, which hadn't been seen before. So the radar here is reflecting off melt streams near the surface, which then when we drilled into were a couple of metres down, but you would never have seen them. And certainly you can't see on any of the satellite imagery. And also some of the other information that we get out of the margin where you're seeing changes in the structure of the ice, which are giving us a better understanding of how the ice sheet margin, and particularly the accumulation pattern in the region, has changed over the last 1,000 years or so. We've got these more straight lying layers along the upper part of the ice sequence here, and then more contorted, probably glacial ice that's been buried in the area below. So these could be potential future targets. And to bring that all together in terms of what that looks like and who's going where, we've got 4 people coming from UC this summer across those various programs. Myself and Rob, who's one of our undergrad students, who just happens to have a whole bunch of experience in drilling and came and knocked on my door at just the right time to help us out with that drill program. Matt, who'll be going on one of the German cruises to go work on some of the raised beach work in the western part of the system. And my former PhD supervisor, along with one of their other folks, Amber, who was again in the right place at the right time to get included on the German program. And we'll be pushing in and collectively with that team over the summer, we'll be collecting material all across that margin to try and work out not just what's happening in the Denman system, but how that relates to some of the other components of that larger area where we're looking at sort of upwards of 10 or 15 meters of sea level equivalent that could come out of this region. So in short, that's, if you've seen me around the corridors, that's why I've been looking pretty haggard over the last 6 or 12 months. And it's also the thing that's likely to keep both myself and a team of people busy across the next, let's say 3 to 5 years. So with that one, I will let Rob come up.
Thanks, Dwayne. Does anybody have any questions for Dwayne?
Am I going to be pessimistic? Only when I'm with you, Ben. So the 20-meter rise in sea level.
Yep.
I mean, I remember reading papers around some of that stuff fairly long time ago, and it always seemed like I presume that's still a fairly controversial idea.
Not for the Pliocene, no. So there are a variety of different records that could, depending on where you are, between 10 and 20, between 10 or even 30 meters. But the central estimate is that sort of 20 meters or so.
Because that's really humongous, given there's about 60, 70 meters of water in all the ice on the planet, and a third of that has melted relatively recently.
Yeah, so 3 million years ago. And the reason why that hasn't happened yet is because it takes a while.
Right.
So you need the climate to have sat at that sort of 3 to 4 degrees above sea level, also 3 to 4 degrees above present day for a period of time, which we don't really have a good idea how long that is at this stage, and probably won't until we start to run that experiment over the next 50 or 100 years.
Sell your land down by the coast while it still can.
That's one option. Yeah. So it could be 100 years, it could be 1,000. We really, at this point, we don't have a good handle on that. And I actually have very little confidence that we will get to the stage of knowing what the answer for that is until we see it. But I suppose and I've also thought about whether or not it's worth continuing to do this sort of work because of that issue. But I think what it does is having the paleo information that this was a problem here. It does help you constrain your ice sheet models because you can then hammer those more effectively in that direction. But also gives you a really good reason to go look at that spot and keep focus on that area in terms of larger monitoring programs to get more of an idea of how things are changing in that area. And do we have 10 years? Do we have 50 years? Do we have 100 years? Because ultimately I don't have a lot of confidence that we're going to stop that happening. But it would be nice to know how to respond to that at a societal level in terms of infrastructure and environmental, I guess, allowing space for the environment to shift in those coastal areas, on those timescales.
You've got ice dirt, and one thing is looking at the composition, right, to see whether or not it's been marine or not previously.
Yep.
It's one thing to do that, but is the dating of that to figure out when it was ice free? What kind of approach will you do to figure out when it may have been absent or not? Yeah.
So for this stuff, for those marginal moraines, the dating is really tricky. So maybe we get some organic material that with some diatoms that went extinct at a particular time, and we can use that as a marker. There is some uranium series techniques which might allow us to understand whether it's in the last 700,000 years or whether it's older than that. But ultimately, I think this particular technique is really showing us where things have happened relatively recently. And by relatively recently, I mean geologically recently. Whereas this one where we're drilling the hole, the advantage of doing that is you have something that's in situ, and that if it was exposed at the surface, which it should have been, well, either you can date using luminescence or cosmogenic dating, or if it's in the last 40,000 years using radiocarbon. So that basically buys us those different options to get a much better chronology, which is why I'm bothering to go to the effort of drilling the hole in the first place, rather than just picking up the dirt off the surface. Yeah.
So is there any stupid stuff on the internet yet about you guys are melting all this ice along these holes? That's why it's melting.
I haven't done an awful lot of publicity on this one yet, so wait and see as we start to do interviews from Bunga Hills over the summer. I mean, stuck there with during bad weather, beaming it back by Starlink. So, yeah.
Okay. If there's no further questions, I'll everyone join me to thank Dwayne Prisoner.
Yeah, that's right. Cool. Yeah, stop recording.